Right, Sadiyah, we'll go straight into your presentation if that's okay with you.
Yep. Hi everyone. Today I will be giving a simplified explanation of quantum entanglement. So what if I told you that there was a form of communication that was effectively faster than the speed of light? There is. And that is the subject of the presentation today, which is quantum entanglement. So before I explain quantum entanglement, I need to explain quantum superposition so everyone knows the full extent of what we are talking about today. So quantum superposition is essentially when a particle exists in multiple states at once. And you might be going, what the hell do you mean by that? But it's kind of like the analogy I like to use when explaining quantum superposition is if you imagine a coin, it's got heads and tails, and if you spin it, it can either land on heads or tails. Similarly, particles like electrons, I will be using the spin of up and down. When they spin, when they rotate, they are existing in the state of spin up and spin down at the same time until we measure them. So that's essentially like when the coin stops. That's when we know whether it is spin up or spin down, or heads or tails. And on the bottom left is a photo of the possible spin outcomes. And that's kind of like saying each electron is directed by its own kind of characteristics, and it's we call it a wave function in physics, but you can sort of say that it's like its description. Next slide. This is a quote by Niels Bohr that I like to use. It's called "Nothing exists until it's measured," and that ties in with quantum superposition. That nothing really is real until we look at it or we observe it. So what is quantum entanglement? So it's kind of like this strange, unexplainable link kind of between two or more particles at a distance that can be light years apart. So if you say there is a electron on Earth and it's entangled with an electron on the moon or Jupiter or wherever, when one changes its spin, like I explained spin before, when one changes its spin, the other instantaneously changes spin. And that's why we say that that information between those two electrons that are entangled, or two particles that are entangled, travels or transfers faster than the speed of light, which is crazy to think about because in physics, there's this established idea where nothing can be faster than the speed of light, but it's been proven that information can transfer between particles faster than that. So quantum entanglement to Einstein and loads of other kind of theoretical physicists was really confusing, and Einstein even called it spooky action at a distance because it went against his ideas that he created himself about physics and stuff. Next slide. So this year there was a Nobel Prize for Physics, and there were three renowned physicists that won: Elaine Aspect, John Clauser, and Anton Zeilinger, and they were all researching quantum entanglement. Now, in their experiment, there was two observers, Alice and Bob, and they both had electron detectors in their hands, and they would randomly rotate like the spin orientation of those detectors. And two entangled particles were sent out in Bob and Alice's directions. They were standing at a distance. The entangled particles were both spinning up and down until they were measured, like I explained superposition before, and they obviously had random orientations on the device. So when those particles reached the detectors, one of them would go off, but the other wouldn't go off because they wouldn't be in opposite orientations. As I explained prior to this, you can have it spinning up and you can have it spinning down, but when you want both of the detectors to beep, you would have to have it so that both particles were spinning in opposite directions. So it's only possible for the electron, when it hits the detector, to be spinning up and then communicate that information to the other electron so it spins down when both of them are measured. And that's when both of the detectors beeped. So yeah, that's how we know that quantum entanglement is actually real. It was proven this year. Wormholes and weird things. Actually, this was a experiment that I was looking into last week, I think. It was only done last week by MIT, Caltech, and I think Harvard researchers. Basically, the idea of wormholes is that they are kind of like a rip in space-time. I think there's a next slide that will show you a picture of one. But wormholes will have information passing quicker through them rather than going around them, which would obviously take more time. So what they did was they got two quantum computers. We call the processors in them qubits. And they're basically like quantum particles in superposition. So those particles kind of formed a 2D wormhole because there was instantaneous information passing through them rather than having to go around the wormhole and travel slower than the speed of light. So the physicists kind of essentially created a holographic wormhole through quantum computers, which is crazy to think about. But yeah, that is what happened. It's not an actual wormhole because if it was, then we wouldn't be here right now. But yeah, that is what happened. Yeah, this is what I was talking about. So they both have this thing called duality, where the wormhole has an easier path for particles to go through than normal space. And as you can see, entanglement is sort of similar because of the way those two particles are linked. It allows them to have information traveling through them faster than light, which is similar to a wormhole. Yeah, I think that is all. Thank you for watching.